Let me introduce, good afternoon, everyone. Let me introduce myself. As Cheryl mentioned, this is Mohamed Ashour. I'm the geotechnical professor of civil engineering at Alabama A&M. And I have experience in research for around 30 years on pile foundations, axial loaded piles, lateral loaded piles, drilled shafts, slope stabilization, soil modeling, soil liquefaction, bridge abutments, and I have numerous publications in national, international journal and conferences. Today, the research we are going to present here is funded by the National Center for Transportation, Infrastructure, Durability, and Life Extension. I would like to thank the Center for supporting this research. And it's going to focus on modeling collapsible soil and its impact on axial loaded piles. Maybe the title here, I put it a little bit ambiguous. So in this case, you said what impact is going to happen to the axial loaded piles. This is what we'll see it when I start introducing the effect or the negative effect of collapsible soil. The presentation today is going to have a number of elements or number of contents. It's going to be, first of all, would like to understand or to know just some background on the nature and behavior of collapsible soils. What type of soil we are dealing with and why it creates problem for us. The second element of our webinar today is going to also deal with the prediction of the collapse potential of inundated collapsible soil based on its initial properties. What's happening here, we would like to model the behavior of the collapsible soil when it is inundated. When it is inundated, it means that the soil becomes saturated and it's going to create problem for us. We will see in the presentation what kind of problems it's going to create for our foundations. And what do you need to know about this soil in order to deal with it, and in order to predict its properties once it's inundated. The third element of this webinar today, we would like to have a kind or establish a soil pile modeling for the collapsible soil. In this case, we will be able to monitor and to measure the negative impact on the axial loaded pile. What negative impact you are going to have? You are going to have additional or a hidden force that's going to act axially on the embedded pile in collapsible soil once this soil is inundated. And that force, we call it down drag force. This means that we are going to have additional force, non-calculated or uncalculated force, that's going to act with the force coming from the superstructure to put more load on the pile and create excessive settlement. Then after we introduce the soil pile modeling that we are going to use it to analyze the behavior of axial loaded pile in collapsible soil, we are going to present a kind of case studies and validation for the model. And then by the end, we are going to have a software demonstration because the model and all of our work has been compiled in a software package that's going to be easy and flexible in use to the designer. Okay, let's start the first one. The first one is the collapsible soil. I understand that some of the audience, in fact, attended the symposium and the paper I presented. And of course, it's coming from this research too. So, but here I'm going to have just 15 minutes or not that enough for me just to say hello. So let me give more details here about the collapsible soil here. So collapsible soil, it's a kind of a soil that maintains large void ratios. And this soil, in fact, it has special structure. So if you take a look at the structure, we see this kind of the particles or the grains of the soil, they are attached to each other through cementations. And this kind of cementation is going to be some clay, some silt. So it's going to put it in a kind of specific shape, and that shape maintains large void ratio. Most of the time, or all of the time, this kind of soil is going to maintain or carry a kind of low moisture content. So it's going to be close to be dry, and it's going to be very sensitive, in fact, to the increase of the moisture or the water in that soil. As long as it's dry, it's going to interact with us in a very nice way, resisting what we need, give us the right resistance. But once this soil is inundated, increasing its moisture, saturating the soil, the structure is going to collapse completely and give us completely different soil. Would you like to see it here? You can see this picture here for the two sides. Here is the right-hand side of the picture, you can see once the soil is dry, loose, it's very nice, provide good resistance. But once it has a kind of source of water, whether that source of water is coming from rains, flood, elevating of the groundwater table, leak, or some water from nearby channels and canals. In this case, this soil automatically under its own weight is going to fail its own structure and then compacted, and is going to suffer huge amount of settlement. This is the source of the problem. The huge amount of settlement or the considerable amount of volume reduction in the soil that's going to lead or cause damage to our structures. Okay. Is it a kind of limited to a certain place? No, it's everywhere. And you can see a map. This is an old map, in fact, that you can see different location for this kind of collapsible soil here nationwide in the United States. What type of soil we are going to deal with? Let's understand also more the structure and the nature of this soil. You will see it here. You see this? This is what we call it the honeycomb structure of the particles. You see that the particles or the grains of the sand, they are attached to each other or cemented to each other. They have bonds there through the cementation of the clay or silt particle there. And look at the amount of the void ratio over there. So, and this is the original structure when it's dry, but once it's saturated or inundated, this structure will be gone and it's going to fail. Would you like to watch it in the lab? Yes, we can see it in the lab. When you have put a sample of this soil in the odometer, you can see it here. Once you increase the stress, look, the volume change is very, very small as long as it's dry. And when you reach at any level of loading, once you inundate the soil, look, under its own weight without adding any stress or putting any additional stress, look at the huge reduction in the void ratio there and the amount of settlement this soil is going to suffer from. And this is a source of danger that we always try to avoid, or at least we consider it in our design when it comes to the design of foundations. The people who are working in the collapsible soil field, they will know that we have a very broad range of the collapsible soil. And in this particular research, we are dealing with specific type of the collapsible soil. What type? We're going to deal with the sandy, silty, sand, and silty soil only. We are not going to deal with the clayey one, because the clayey one, in fact, they have different behavior. So we are dealing with, in the collapsible soil here, which is very common to this type. You will see it here. Let me see if you can see the mouse. Sorry for that. Yes, if you see it here, you can see that we are dealing with soil. Mainly, the main grains are sand, and they are attached or cemented together through a kind of clay bond or silt bond. This is the type of collapsible soil that we are going to deal with. Right now, we understand what happens to that collapsible soil when it is inundated. Okay, what is the impact of this inundated soil on the piles? What happened that when you have the soil surrounding the pile and the soil out of the sudden or even gradually is suffering a kind of large settlement, and that settlement of soil layer is more than or larger than the settlement of the pile, this means that the soil is taking the pile down with it. It's putting additional force on the pile and pushing the pile down. And this is what we call it the down drag force. So in this case, it's not normal to have the soil settling more than the pile. Usually we put the load on the pile and the pile is settling more than the soil. In this case, the soil is going to provide resistance, upward resistance to the pile movement. And this is what we call it the positive, and this is what we call it the positive skin friction. This is normal. But when the soil is settling more than the pile, this means that it's going to create something different, which is called negative skin friction. This negative skin friction means that we have shear stress working downward on the skin of the pile and forming a down drag force acting on the pile in addition to the external load at the pile head. That's why I call it a hidden force, because you do not see it, but it's working there. Does this happen only with the collapsible soil? No. In fact, we have different scenarios that happen. And even the Ashour addressed that, the FHWA addressed this problem by saying, okay, the major three scenarios that we have them in reality, the major ones, that when we have, for example, a case like this, we have we have clay layer here, the light one here, and we put a fill on the top of the ground surface, like what we have in any construction site or bridges, things like this. So you have a road or ramp or something like this. So once we have this kind of fill, This clay layer, as all of us know, is going to suffer consolidation settlement, and this is going to happen over the time. So when this clay layer is settling there, it's going to take the overlaying layer with it, and compared to the amount of settlement of the pile, in this case, down drag force could take place, and we're going to have negative skin friction. This is one scenario. The second scenario, and in the West Coast, all of us know that, is the soil liquefaction, especially in the state of California and the state of Washington. So we'll see that when we have soil liquefaction, what happened that the liquefied soil is going to have excess water pressure, and post-liquefaction, the excess water pressure is going to dissipate, and the liquefied layer is going to settle, or going to be settling, and the volume change is going to change due to the dissipation of the water. So that liquefied layer is going to suffer also significant, especially if it was loose sand, is going to suffer significant amount of settlement here. Create what? Negative skin friction and down drag force. Wow. And you can see here that we have two types of skin frictions. Negative skin friction for the part of the soil layer that they are settling more than the pile, and we have positive skin friction for the lower layer where the pile is settling more than the soil, which is the normal one. This is the resisting one there. The last phase that the last scenario that we are talking about is the one that we are handling in our research, which is what is the one when we have collapsible soil. When we have collapsible soil and that layer has been inundated, in this case, again, considerable amount of settlement here. Soil is going to settle larger than the pile, negative skin friction, down drag force. Okay, now we can see the problem clearly. What should we do to deal with this problem? Number one, we need to develop a correlation or a kind of a relationship that allows us to measure or calculate the amount of volume change in the soil when it's inundated based on the initial properties of the soil. Without measuring or determining the collapse potential of the soil, once it is inundated, in this case, we will not be able to calculate the amount of the soil as the settlement of the soil, and will not be able to calculate also the down drag force on the pile. And this is the negative impact on the pile or destructive impact. This is number one. So we need a correlation to do this. Number two, in order to analyze the pile under any axial load, we should have a soil pile model. We call it the TZ curve. And all of us, of course, in civil engineering, we know that, how to calculate the interaction between the soil and between the pile and the surrounding soil. We have this one too. And the third element that we needed to, or component that we needed to analyze the pile under axial load, we need to have also a kind of, they call it the QZ model, which is the tip resistance of the pile. Okay. Also, in order to deal with the negative skin friction, as I mentioned before, we should develop interactive soil pile model to detect and determine the down drag force acting on the pile. How much the down drag force, where is going to happen on the pile, and in this case, once we consider it, what is the response of the pile, how the pile is going to react to that force. And then the fifth one that we have it there, we need to validate the proposed model. Of course, this work, we cannot start this model, this work from scratch. This is a kind of very lengthy phase of work, and we should have work done before. Of course, the one that we are going to do it is going to be the correlation of the collapsible soil in order to assess its properties. The second one that we are doing here is establish a model for soil pile interaction to detect and determine the down drag force on the pile. And the third one that we are going to do the validation. The other two, it's already, we finished them years ago, a long time ago. It was part of our research and how to analyze, to develop a TZ curve or to get a QZ curve. This I'm going to show it to you just in a moment. So this is exactly the kind of five components that we need to have in order to perform this kind of analysis. And these are the three ones that we are presenting in this research phase. Let's start with the first one. The first one is dealing with the collapsible soil itself, regardless if it's going to be, it's going to have a pile or foundation, shallow foundation or whatever. We would like to assess the collapse potential of the soil when it is inundated. So the only way to do something like this with different types of soil, random sample that we have it, is to collect experimental data. And I would like to thank the other researchers really who publish their data regarding experimental data for the behavior of collapsible soil. And we developed this kind of empirical formula. I'm going to explain it just in a moment. This empirical formula, we'll see this is the CP, which is the collapse potential. What is the collapse potential? Let me jump to the next one. It is in a simple way. Here's the definition of the collapse potential. It's how to measure the change in the void ratio of the soil. And in this case, I can calculate the amount of settlement of this soil when it's inundated. Okay, what parameters affect the collapse potential of the soil? We have four parameters here, or four properties. One of them is the overburden pressure on the soil. How much overburden pressure this soil is having. I mean that the depth of the soil, in fact. This is number one. Number two is the initial degree of saturation. How much is the saturation ratio of this soil, the original saturation ratio of this soil before we inundate it? Of course, usually it's very low, 10%, 15%, 20%, something. And this parameter is very effective too and very influential here. The third soil parameters we need to, or we consider it in this model, is the initial void ratio. As I mentioned earlier, I said that we have honeycomb structure that maintains large void ratio. Yes, you'll be able to see it here. And this is the one that's going to also be the source of the significant or large amount of consolidation, settlement once the soil is inundated. And the fourth parameter that we discovered not that effective, they call it the uniformity coefficient of the collapsible soil. So we collected or studied this kind of four parameters here that we can see it, and we put them in this formula. This is a kind of empirical formula that allows us to do this. Here is a comparison between what? Between the calculated one, this formula, the CB determined from this formula, and the measured one that you can see it down here. And this is the experimental one. And we have this nice formula with good, in fact, coefficient of correlation, R square 0.81. It's very nice to have this kind of agreement. Take a look here how we did this. We have, in fact, large Excel sheet that collected the data for more than 250 samples, tested different types of soil. And you can see here the site, sand and silty sand and silt, all of this kind of soil. And based on initial properties and the CB for that soil, when they are tested in odometer. And we collected this data, and the one that used it, in fact, we use this data to develop or establish the correlation that we saw before. How we did this, in fact, we studied every element or every property independent from each other to see its impact on the collected CP, the collapse potential. Here is an example. Here is the variation of the saturation ratio, the initial saturation ratio of the soil. We see that how the difference here, its impact on the collapse potential. And you see that the larger the degree of saturation of the soil, the less the collapse potential, which is normal because the drier the soil, in this case, the larger the settlement that the soil is going to experience when it is inundated. And we notice that if you are dealing with collapsible soil with initial, let's say that initial degree of saturation around 60% or large, you do not have to expect any collapse potential to happen. So you do not have to expect a kind of significant settlement for that soil. No, it's going to be, but we are dealing with dry soil, 10, 15, 20, 30% initial void ratio, so the initial saturation ratio. Once you inundate the soil, yes, you should expect to see a kind of larger settlement there, and to see, of course, if you are studying down drag, to see more drag force acting on that. Here is another case when we are studying the second parameter, for example, that we have it there, when we are dealing with the initial void ratio of the soil, and we can see its impact on the CB. So we studied every one, and we tried different relationship or parameter in order to develop the empirical relationship that you see there with this good level of coefficient of correlation. Are we the first one to do something like this? Of course not, because we have other researchers, in fact, who already conducted similar research like this, but using different parameters and develop different correlations. But if you take a look at the parameter, you'll find them siblings, some like cousins. For example, here they are using the water contents. For example, this is the Parpasma and tensor 1992. Here I'm using, and you see that this is the water contents that you can. I'm using here the degree of saturation. There they have the conformity coefficient. They are using the vertical effective stress. Yes, I'm using there the, for example, the void ratio. So you can have it here. It is a kind of mix of gamma D and the water contents. So try to be very direct here when you are dealing with the important and significant properties. You will see that this kind of properties mainly, or this kind of behavior is mainly controlled or governed by the void ratio. The void ratio, the initial void ratio, and effective stress and the initial degree of saturation. Now we have this relationship that will allows us to calculate the collapse potential. Okay, so what happens? Remember that when the soil in fact collapse, inundated and collapse, it's not the original soil anymore. It changed. It has been compacted. It has different void ratio. It's going to maintain different friction angle, which is very significant for us. So we need to calculate the new friction angle for the soil. So we use this chart from the DM7. It's a very well known one for geotechnical engineer. And based on the new void ratio, the horizontal axis here, I can, on the type of the soil, I can calculate the new friction angle. Yes, this is a strength parameter. I will use it in the design, in my design, to calculate the negative and positive skin friction of the soil. This is one. This is for collapsed soil. Also, based on the new void ratio, I get it, I will be able to calculate epsilon 50. Epsilon 50, it's the normal strain of the soil at 50% stress level. We use it to build our model for a strain curve of the soil. I mean the constitutive model of the soil. So these two curves allows us to get the new properties of the soil. Now, once we are done with the modeling modeling the collapsible soil, let's go to the next phase. What is the next phase? Piles. Piles embedded on this piles embedded on this soils is going to suffer a kind of negative skin friction and down drag force. We need to deal with that. A second model that's going to develop. So we are going to develop soil pile modeling. How it works? Of course, this is a standard model that was developed maybe 50 years ago about how the pile is subject to axial load, and then you have skin resistance, which is the TZ model, and you have tip resistance. So the point here is how the pile is going to interact with this soil that is settling next to it. Okay, what is that? Look here at this model. If you have a kind of collapsible soil layer here, and you have overlaying soil over there, and we have the pile there, and we have a stiff soil there, and we have axial load acting on the pile. Look here. This is a kind of collapsible soil that's going to be inundated and settle, taking the overlaying soil layer down with it. So in this case, these soil sublayers, I'm dividing the soil layer into sublayers, and also the pile. I'm dividing the pile into small segments equal to the thickness of each sublayer. So what happened that as long as these soil sublayers they are settling more than the pile, look here, this means that they are going to create negative skin friction. And it's going to decrease with depth until I reach a point where the situation is going to be reversed. How reverse it? The pile is going to be settling more than the soil. In this case, I'm going to have positive skin friction. Our modeling, in fact, the model that I'm going to show to you is going to track this kind of behavior to locate where the negative and positive skin friction are going to develop on the pile skin in order to do this. In order to do this, we do it in a mobilized fashion, in incremental way. So if you are dealing with the soil in mobilized fashion, this means that you have to have a stress strain curve. This is our stress strain curve that was developed more than 20 years ago, and we use it in many research, published research. This is number one. Number two, this is also our TZ model that we developed before. We are using in the analysis model. This is a list of the publications that already address this kind of constitutive model or soil stress strain curve and the TZ model. Okay, now we can characterize the problem. We have the tool or the tools that will allow us to analyze or to build that model. Another question, what do we have right now in practice? So if you are performing research, this means that you are taking additional step toward, compared to what we have right now. So we have to take a look at the current practice and to see what the current practice is doing and what we are doing extra here. Is it the same or something we're taking additional step to improve something? This is the pioneering work, in fact, done by Felinius. It's a great work. It has been there for a while, and it's addressed by the Ashour and detailed in the FHWA. How they deal with the negative skin friction in general, the down drag force in general, regardless of the source of the down drag force, whether it was coming from the consolidation of the clay or coming from the settlement of liquefied soil or coming from inundated collapsible soil. It happens regardless of the source. So when you have a situation like this, you will see that this is what they are doing. The technique is asking you to do, here is the pile length, and you are going to go, and here is the value of the axial load acting at the pile head coming from the superstructure. And then you are going to go and perform, you will say, here is the negative skin friction, the ultimate negative skin friction that could work on that pile, going down until you go down to the pile tip. And here is another curve that is going to show you or determine the ultimate positive skin friction, resistance of the pile from the tip till the top. So this is the resistance. This is the upward resistance. This is the downward force. When they intersect at certain point here, they call it the neutral plane. This means that this is the balance. It means that there is no negative nor positive skin friction. So what happens here, the portion or the segment of the pile above the neutral plane is going to be subject to down drag force. The lower part is going to be subject to resisting force. And this is how we calculate the down drag force on the pile, the neutral plane, and the resisting one. It looks very nice. There's no problem with that. But in fact, we have some limitations here. The limitation number one that you can see it here, that the analysis that we perform right now, it's not the actual problem. It's not the realistic one. It represents the ultimate situation. The same like I'm telling you, this pile can take 200 kips, but in reality, you are just putting 100 kips. So how much is settlement in this case? You need to calculate the settlement of the due to or caused by the 100 kips, not the 200. So this analysis is dealing with the ultimate situation, regardless of what you have right now. This is number one. So we need to deal with the actual situation to determine how much down drag force this particular pile can take for that situation. Second limitation, the user is supposed to play with the pile length in order to move the neutral plane to the desired depth. What does it mean? That the location of the neutral plane is going to change based on the length of the pile. So it's going to move up and down based on the length of the pile. And as a designer, I assume, of course, the length of the pile to meet my requirements. But I know for sure that the neutral plane is supposed to be close to the bottom of the collapsible soil or the bottom of the consolidated layer or the bottom of the liquefied layer. So in this case, I have to change the length of the pile to balance the negative and positive skin friction in order to get the neutral plane at that position. So it's a kind of back and forth calculation. This is one. The technique we are doing is not doing this. It gives you what you have there, and it's going to give you at the right location. The soil above and below the neutral plane is fully mobilized. Yes, because you are dealing with the ultimate capacity. In our case, we deal with the actual load. So the soil may not be at some location not fully mobilized, meaning that has not reached its ultimate capacity. So this is a realistic situation. The last thing, which is really a problem for the designer, that the pile tip resistance here, this technique does not calculate it. You assume it. So you say, I'm going to calculate the ultimate resistance of the pile tip. This is the maximum load that that pile tip can take at that depth. But is this the real one? You do not know. So in this case, you have to assume what is the percentage of the pile tip is going to be implemented in this analysis. Are you going to use 100% of the pile tip? Is going to affect the shape of the curve and the location of the neutral plane. Are you going to use 50%, 1/3? So this is something uncertain here. So in this case, you have to assume the pile tip, but in reality, there is a specific value or there is a particular value based on the axial load and the length of the pile, all of this parameter, that this pile tip can take it. You need to take it in order to have representative analysis. These are the main limitation that we are considering here in our analysis. How the technique is working, as I showed to you before, let me show it to you here. Okay, how the negative skin friction is tracked in that interactive model. Here is the model. We divide the length of the pile into pile segments. Okay, you are going to have around 100 segments like this. I'm just putting some of them here. And every segment in here is going to, of course, having a kind of TZ side resistance from the pile subject to axial load. So we know this for sure. When we solve the axial loaded pile, in fact, we do not solve them from the top to the bottom. We solve them from the tip to the top. So we start with the segment at the tip here, that by starting assuming or starting with incremental fashion. So we solve the pile, or we analyze the pile with the soil in incremental fashion. What do you mean incremental fashions here? I start loading the pile gradually with small values and then increase this value gradually until I capture the balance I'm looking for. For example, here we start with segment 1, assuming that we have very, very small level of loading here, and then we move from segment to another to study the balance with the surrounding soil until we reach the top. Okay, we reach that balance. It's not equal to the axial load over there that's already there. It's coming from the superstructure. We increase the tip capacity and resolve again and so on. While we are doing this, we can go back to that shape. This is the pile. Why it's tilted? Because here we are measuring the settlement of the pile head, and here the settlement of the pile tip. It's measuring horizontal here. Okay, so that's why I see it inclined. We start comparing for each pile segment. We see how much settlement this pile segment in that particular solution is suffering compared to the soil settlement. If the soil settlement, which we calculated already earlier, is larger than the pile settlement, I'm going to have negative skin friction. You go to the TZ curve here, based on the settlement, you can get the negative skin friction on the pile, and so on. So for every pile segment, you compare its settlement to the soil, surrounding soil settlement, to identify if you have a negative skin friction or positive skin friction. You can see here, look here at the settlement of the soil. It's decreasing with depth until I reach the neutral axis. Then it's going to switch to have soil settlement less than the pile settlement, so you have positive skin friction. So it's again very large back and forth iterative process in order to capture the actual negative skin friction or down drag force acting with this pile. You will notice something: whenever you change the pile head load, you are going to have a change in the neutral plane because the pile settlement is going to change. So its interaction with the soil is going to change too. So this gives you an idea. And this is the force distribution, the pile head load that you put it there. If you do not put anything, it's going to start from 0. So the pile head load, the axial load, and then you can see here is a down drag force increasing with depth until you reach the neutral plane, and then you're going to have the positive part where the soil is resisting the load, and here is the tip resistance. This is end bearing. It's calculated based on what we have. I know it's a kind of lengthy process here. We have a flow chart. I'm not going to go through it, but that lengthy chart, in fact, is describing every single step we do through the iteration process, including the input and the output data. Of course, we are going to let the designer or the reader to go through this kind of lengthy, tedious process to do it. We do have a software. So we have a package. In fact, for that, I'm going to demonstrate it just after I finish my presentation here. And that package is going to show you how to use the program. Very friendly in use to put the input data, get the output settlement, so reduce the human error tremendously here, and we can show the capability of the technique here. Last phase I would like to hear is the validation. This was an uphill battle for me, in fact, because having or finding in the literature a kind of full-scale bio-load test embedded in the dated soil, it's something very, very difficult. Okay, so this is something for sure. I'm really encouraging anyone to find a test like this, full-scale load test, to let me know where you can find or give me the access to that one so I can reach it. The two tests I found at full-scale tests, I found them in Russia. So this is what we have. This is in a book by Gregorian in 1997. They performed very good full-scale load tests over there. Okay, and even those tests were used by other researchers here in the United States. for validation too. They were using a kind of development numerical analysis using experimental test. I will show it to you in a moment. And this is the profile of the soil that they are dealing with, the depth of the soil. And from 0 to 8, this is the collapsible soil. Okay, take a look at the collapsible soil here, that you have it here. You will notice that if you do calculation that the initial void ratio is 20%. Okay, and they put a pile there. The length of the pile is 22 meters. The diameter of the pile is 0.5 meter. Okay, and the collapsed soil, the soil that they inundated in that thing, was the upper 6 meters of this 8 meter collapsible soil layer. Okay, so they inundated the soil, the upper 6 meters. So inundation in this case, or saturation, was from the top to the bottom. Remember that, because the inundation of the soil could happen from the top down or happen from the bottom up. If you have elevation or rising in the groundwater table, in this case, you are inundating from the soil from the bottom up. If you have flood or source of surface water, in this case, you are inundating the soil from the top down. This one, they use a very nice way to inundate the upper 6 meters of the soil. They have a pit 20 meters by 20 meters around the pile and depth 1 meter. And they kept the water with a height 0.5 meter in that pit for 2.5 months. For sure, this kind of the vicinity of the pile or the soil layer around the pile will be saturated and inundated fully. So this is something really appreciate doing something like that. What happened in this case? You can see this is a technique with comparison between you see that they obtained down drag force on the pile due to the settlement or the collapse of the collapsible soil due to the inundation. There was an additional 186 kilonewton coming from the down drag force, plus what? Plus the pile head load, which is coming from the superstructure. I mean the axial load that the pile had. And they give us the experimental data for the CP. And of course, this is the initial saturation that we used here. Here is what we get from our program. You can see it here. Look here. This is the pile head load, down drag force. We obtained, in fact, 183. It's a kind of good luck to have this kind of accuracy. Usually, we do not get this kind of agreement in geotechnical engineering. When we have 20% difference, is going to be something very good. So measure down drag force here, 186. Here 183, okay, using the data, reported data there. Take a look at the variation of the CP. This is what we measure, because we measured every soil sublayer, I mean every pile diameter. So the variation of the CP, it changes from around 2.7 down to something like this over the upper 6 meter, which is the inundated soil. Here is the value that they gave us. They said that the CP is around 7. I do not know where they measure this one, but it's very close, because the CP, according to our technique, is going to change with depth because of changing the overburden pressure. So this is something really good comparison, but one test is not enough to validate any technique. And this is a comparison between, this is a soil settlement. You can see, look at the amount of settlement. This soil had settlement around 340 millimeter. Okay, around 34 centimeter, which could be around maybe say what 20 around how much is this one? Could be around 12 inch maybe, or 13 inch, something like this settlement. And look at the settlement of the soil with depth. It's going down, decreasing until it reaches 0 at around 6 meter, which is the bottom of the collapsible soil. This is the pile and its settlement. You can see here is the location of the neutral plane, and this is the positive part. The program gave you this result directly. You do not have to play with it, and give you the amount here in this table. You can see, let me move this thing here, and you can see here is the predicted value. Here is the pile head settlement. The pile head settlement under the axial load, the pile head load, and the down drag is going to be 17.8 centimeter, millimeter, and the depth of the neutral plane, you will find it there. So this was good comparison. The second test was different story. The second test that those guys had, in fact, it's like this one. We have a pile 18 meter, and that pile is embedded here, and it's 1 foot diameter. And the collapsible layer, in fact, it was deep. It was from, if you check it here, from 6 meter to 15 meter. This is too deep, and you can see it here, there. The inundated, in fact, the bottom 4 meters of that layer from 15 to 11. This is what they inundated. But the inundation here was from the bottom, and it was using different procedure to do it. What they did, in fact, they had a kind of drainage hole, around 3 drainage holes, and they could start pumping the water into this drainage hole to saturate or inundate the soil here. Of course, without any comparison here, we should say that inundation here will never be complete. And because this is not enough to saturate all of this area and to make it inundation with over there to create collapse. So for sure, regardless of the results, I'm not criticizing their great work, but this is kind of the condition of the test. So you cannot maintain full collapse because you cannot maintain full inundation for that soil layer at that depth. And also you will notice something here. If you see it here, you will see the degree of saturation is 56, which is very, very high, the initial saturation. As I mentioned before, based on experimental data, the larger the degree of saturation, the less collapse potential you should expect. This was close to 60% initial saturation, which I said that will not provide significant settlement. So this is something really different. Some comments about that test here, the CB. If you check here, sorry, and the CB that they got it was 8. The CP we get it from our analysis, it was around maybe 1.5, something like this, which is consistent with these results. But there should be something in that test. I'm not saying that it's wrong. I'm just trying to explain to you the differences of the results between what we got and what they gave. And I'm not saying that they are wrong or we are right, something like this. I'm just trying to highlight or underscore the source of these differences. So the measured down drag force that they provide was 740 kilonewton. The one that we calculated was 1,275, much larger. And they explained the reason, because we are both of us are going in the right direction. We are supposed to predict values much larger than them. Why? Because the inundation was not complete over there, and the saturation, initial saturation they started with was very small. Sorry, was large, and we should not expect that much collapse over there. Here is what we got from our program, and you can see if you calculate this value, you see it's 1,275 compared to the 750. It's larger than this. Of course, there is another reason that the geotech specialist in geotech understood this. We have arching effect here. The deeper the soil, the less settlement that you can carry to the ground surface. This is another story that could affect the results here. So the last test that we have is experimental tests. I looked for that one. This was in Canada and by Ashour and Hanna in 2016. To be honest with you, I'm not a big fan to experimental tests when it comes to pile foundation, because the scaling factor, when you are reducing the size of a pile to have it like 2 feet length to embed it in the soil. So we scale the pile, but we do not scale the soil. We scale the pile down, but we do not scale the soil. So in this case, the soil pile interaction is going to be affected tremendously, and the results could be highly influenced by this. But this was good test. In fact, it was a good step to do it. And they put really great effort here, and really appreciate putting this test here. They saturated also the soil here, and we tried to calculate the down drag force. For the sake of time, I'm going to try to be brief here. And we obtained the value 133 kilogram. The value they calculated was around 120 something kilogram. But this is for one test. Okay, they performed around 4 tests. I did not get good agreement with the other tests. Why? Because what happened that in that particular test, they are not only inundating the soil. No, they are applying pressure on the ground surface to create overburden, which is going to also create settlement in the soil, but not from the inundation, and also create down drag force that's not coming from the inundation. So things are mixed here. That's why I cannot claim that I can get a kind of good agreement with this. This is just a kind of lucky shot. I can consider it like this, but I use the input data, the right input data, and I get it this way. For the other tests, when they change the inundation, because they were inundating the soil under pressure, this is another factor that could affect the results. So this is just a test I want to show, but it was a very good test. It's a very good step in that direction. In order to conclude what we are doing here, here is the conclusion that we can present here, that the study presents a model to determine the CP, the collapse potential of the untitled soil, based on the initial properties of the soil, which is a very good step in order to predict or calculate the amount of settlement for the post-inundation situation. This is a very good thing that we can gain out of that. And also, one of the observations that we can address here, that if the collapsible soil maintains large saturation ratio, like more than 60% or more, you do not have to expect significant collapse potential for the soil, and you should not expect a kind of significant down drag force on the pile. The other thing that the interactive model that we are presenting, in fact, can predict or allow the prediction of down drag force acting on the pile in a realistic fashion, okay, and can provide you the response of the pile in a mobilized fashion too. So in this case, we'll be able to see better picture about the response of the pile under down drag force. The other thing that the variation of the axial load at the pile head influences the location of the neutral plane. Of course, we know that, which is something, and depends on the soil pile relative settlement, which one is going to be larger than the others. The other thing that, the last thing, that additional full-scale field tests are still needed for more validation for the proposed model, which is something for sure that we needed more. It's not enough to deal with 2 tests only. Let me take you right now to the program to show you something. Let me share this. Let me stop the sharing and come back. Okay, how can you do this? Sorry, stop sharing. Let me share the program here.
I think you go with the advanced sharing options in the share screen.
Let me see.
Yeah,
yes,
okay.
Can you see this? Can you see this right now?
Yeah, we see the screen, but let's see.
Can you see it?
Yeah.
Perfect.
Great.
Okay, here's the program, the page of the program that you can see it here. I can upload one of this file. So let me get the Nicopol one, which was the best one that we have it. You can see here, in this case, we can provide, in fact, the soil, the type of the soil that we have. You can choose the type of the soil based on whatever. So we have here sand, clay, different types of soil. So you can choose the type of soil that you are looking for each layer. And you can provide, of course, the location, the bottom, the depth of the bottom of that layer. So in this case, you can get the soil profile, the unit weight of the soil, the friction, initial, all of these initial properties, the initial friction angle of that soil. If you have cohesion, you can use it too. And you can mark it if this soil is collapsible or not. So it depends on if it's collapsible. In this case, you will be able to provide the void ratio, degree of saturation, uniformity coefficient. If it's not, you cannot access these things. So I'm trying to keep the user on the right track, because not every user like the other, not each one like some, they could be very professional using these things. Some will just be a kind of using this just for some time and they leave it. So this is a kind of profile of soil. If you would like, I'm going to show it to you right now. And then you have the different types of pile that you can choose. Square concrete pile, circular concrete pile, steel pipe pile, H pile, because we have different type, and you can provide the properties, geometry of that pile, the perimeter of the pile, cross section, the area of the cross section, the depth of the pile tip, and the location of the water table. And then if you would like to see your profile, you can see it this way here to review what you did there. So I'm trying to reduce the human error to the most, or to the lowest case I can do it. So in this case, do you have axial load on the pile? You can provide the axial load on the pile. The tip efficiency, would you like? Because sometimes we can say that we are not going to rely that too much on the pile tip. I'm going to use just 50% of it, but I mean that I'm going to use a mobilized fashion of the 50%. So 50% is going to be the full one. So in this case, when you have a situation like this, and they provide my properties here, I can go and perform the analysis. So in this case, what type of analysis would like to have it, with down drag or without down drag? So I'm going to use the pile down drag force. And look here, you are going to have the load. By the way, here I'm using, this program is working with US units, imperial units, not the kilonewton, not the SI units. So you can see here is the load at the pile head. You can see it here. This is 135, the pile head load. Here is the down drag force. And then you reach the neutral plane. Look here at the bottom here. Once you run it, you are going to see these results. So you don't have to calculate anything. This is the depth of the neutral plane at 19.44. It's in here from the ground surface. The pile head settlement, 0.57 inch under this, the axial load, both of them, the pile head load and the down drag force. The amount of the down drag force here, you can see it, which is from here to there. It's around 42 kips. And of course, the total axial load is 177, which is this plus that. Okay, so you can see there. What do you need to see else? You can see also here is the soil settlement because of that inundation down to the point of the intersection. Here is the location of the neutral plane, which is 19 something. As you see it here, here is the pile settlement there. What do you need to see else? You can see also here. Here is the pile head load settlement curve. Sorry, the pile head load settlement curve. You can see that with the increasing load. What you see here, this is the beginning. This portion of settlement is caused by the down drag force. And that's what I'm saying, it's a hidden force. It's not a load that you put it at the pile head. It's a load generated by the soil. So in this case, the soil caused that pile without any pile head load, this amount. Okay, and then due to the presence of the axial load, you can see that the pile settlement is increasing here. How much is the pile head load? You can see it. I already loaded until the end. What is the end here? 130. You can see here 135 kips. This is the axial load, and this pile is settling under both components of loading this amount of settlement, which is 0.5784. So in this case, the designer can do whatever he or she wants to calculate. Would you like to change the length of the pile? Of course, I can change the length of the pile to deal with different length of the pile. For example, let's have it, I'm going to have it say 88, say something like this. But look here, when you increase it 88, you have to look at the profile. Luckily, my profile here is going down to depth to 91. I can increase it to 100 and then go to the profile. Okay, so I increase the length of the pile. I can run the problem again for another case and so on. So this is the thing that we have. You can get all of the output file that you needed here, for example, as an output organized, and you can get your results in a very nice way. You can document what you need. I believe based on the time, I'm in a little bit late, so I welcome any question, and I would like to thank all of you for listening and for any question that you may address it to me. Thank you.
Thank you, Dr. Ashour. Dr. Panelides does have a question for you.
Sure.
He says, thank you for the interesting presentation. What does a collapse potential of 25% mean? Is that a high likelihood that the soil will collapse?
Okay, the collapse potential, 25% mean that 0.25. There is a difference. If you, is it a decimal value or a percentage? When you said that 25%, this means this percentage. This means this value is going to be.
No, it's I think you had it as a decimal. I'm sorry, decimal.
Okay. Decimal, okay. 0.25, let me give you an idea about to connect the number with the collapse. Okay, the collapse potential, there is a kind of a table or standards that classify the degree of potential, I mean collapse potential. I do not have the number in my mind right now, but if, for example, if your collapse potential less than, for example, 1.5, you call it a low collapse potential. If it's between, for example, 1.5 to 4, you call it moderate collapse potential. If it's more than that, you call it severe collapse potential. This means that this soil is gonna suffer large settlement. If you would like to know the exact value, how you can get the exact value, here is the equation I showed to you here to get the collapse potential. Look at this one. Okay, collapse potential means that
I'm not seeing anything, Dr. Ashour. I'm not seeing anything.
Who say, oh, I'm sorry. Don't you, oh, let me, just a moment. Just a moment. Let me stop the sharing and get the new share. Just a moment. Here is on. You should be able to see that one. Can you see this?
Yes, I can see it.
Okay, that's perfect. Look here. This is, so we have a classification or categories for the collapse potential. From this range to that range, there's going to be low collapse potential, meaning that the soil is going to suffer small amount of settlement when it is inundated. Okay, from that range to that range, I mean, by increasing the collapse potential, this means that the soil is going to suffer larger amount of settlement or deformations. How to calculate it? Here it is. If you have the collapse potential, say in a number 2.5, for example, 2.5 here, and we have the initial void of the ratio, is going to give you the reduction in the height. So if you have, for example, 1 meter thick soil layer of 1 meter thick, in this case, this delta E is going to give you, for example, a value which is initial void ratio equal to 0.25, and as a percentage of that 1 meter. Do you see what I'm saying? Look at here.
Yes.
Yeah, here it is. Delta H divided by the HO, which is the 1 meter. So in this case, we can calculate the change in the height of any soil layers based on the collapse potential. That's why it's a key parameter.
Okay, thank you.
We have another question from Dr. Shi. He says, very intriguing presentation. Thank you, Professor Ashour. One question is that knowing the key influential factors in the empirical equation you developed, can we potentially proceed to developing some sort of mechanistic model incorporating these factors?
Okay, this is a kind of something I tried to do this, to be honest with you, but not through myself, to be through one of the students, my students. And there was a software, let me see that can do something like this. But to be honest with you, when we did it, it gave me a kind of correlation that I could not use it. So what I did, I went back to the old-fashioned way of modeling, which is dealing with this kind of the parameters individually, one by one, to study their impact on the CP. And I relied on the measuring my success in the modeling here by comparing the results I obtained from my correlation to the experimental results, as I said, as I showed over there. So I'm not sure about this as going to be successful or not. Am I answering your question, or you meant something else?
Oh yeah. I just a thought, since they are known to be crucial in, predicting the collapse potential, they may, I think eventually we'll get there, right? With some sort of modeling, mechanistic model.
Yeah. But I need also to highlight something here. It's soil. So soil here is not a man-controlled material. As you know, it's different from the concrete when we deal with it. So you cannot have a kind of certain trend that's going to cover all of the soil. You can get similar soil, but with a scattered response. Okay, something like this. That's why you always try to get a kind of general trend of the soil. It doesn't mean that is going to cover all of the type of the soil. You can see it here. For example, this is considered, if you can see my screen here, this is considered very good agreement. And when it comes to soil, we are dealing with soil with material that non-homogeneous, non-uniform, non-isotropic or anisotropic, and we deal with this kind of material assuming that it's homogeneous, isotropic, and uniform.
Right. We deal with similar issues in concrete materials where it's heterogeneous, and so many of the service life models or risk prediction models are somewhat stochastic.
Absolutely.
You have confidence levels and so on. Like say in this case, if you draw a confidence level, I don't know, 85% or whatever, then pretty much the vast majority of data points would fall within that.
Exactly. But maybe you are more lucky than me, because in the concrete you can stretch your hand and change some of the components of your mix, and he said I'm going to improve the quality of this concrete to have it this way. But in soil we deal with what we have, so maybe you are more lucky here when it comes to the making your own materials.
I guess I'll also read my other two suggestions. One of which is I'm a little bit paranoid about units, I guess. So one suggestion is you could make each factor unit less and then develop the equation so that on the left side versus the right side, you don't have the trouble with different units. I'm sure you can easily do that. I mean, just units.
Yeah, but keep in mind that they shoot each other. Let me put it this way: what do you mean shoot each other? When you try to improve one of these parameters to be in very good thing, it affects the other ones. Do you see what I'm saying? So they are shooting each other. So it's something. Yeah. Yeah.
Another thought process is, we're doing some neural networks.
It's breaking a little bit
lately, and in your case, I think again, this equation may not be the final answer. It's just a very good solution. So I know neural networks are really good at developing predictive models based on noisy data. So in other words, in a way, the neural networks or machine learning may help you find a function, a form of function that might work even better than this. I'm not suggesting a black box approach. I'm suggesting, we still have some equations. It's doable, but with the help of
you remind me of something. This is exactly the technique that my student used. Yes, this is exactly what he used. Yeah, if I can show you, I still keep the program here on my computer.
Okay,
on the screen. Yes, we call it equa family. Let me show you this. Let me stop this just a moment. Yes, this is the one that they are using there. Just a moment. Let me put you on that. New sharing. Okay, where is that? Just a moment. Oh, come on.
I think you need to stop share this one before you move on to the other.
Oh, it seemed like I have to stop sharing. Yes, you are right. So let me get this one. Okay, and let me get the new one. Share. Okay. Oh, I don't see it. Why is it? I already ran the program, but it's.
You run the program. Yeah, I think you have to do that advanced sharing option because you cannot just share screen. Otherwise, we won't see it.
Okay, here it is.
You have to stop sharing and.
Yeah, this is something. Okay, here it is. Sorry for that. I'm sorry. Okay, stop sharing here. No, I cannot. I don't know why I cannot. I believe
that's okay. That's okay.
Yes, here it is. Here it is. I got it. Okay, can you see it?
It's coming up. Yeah.
This is the one that we used it here to provide the input data. And then we left the program, for example, overnight to try to find different formulations with different parameters there to give us this kind of random empirical formula.
Oh, I see. Yeah.
So it has different things. Yes.
So we have the same thought process.
Oh yeah. But to be honest, I was not good in this. My student was good in it. Yeah. So he came up with this idea, trying to find a kind of more scientific, as you said, scientific way to develop a kind of more consistent formula or relationship instead of the trial and error way that we used to use it.
Yeah. One thing maybe from the statistics point of view, I don't know whether or not your student or your team had done this. Like in addition to R-square, you may want to look at the residual plot to make sure it follows a reasonable distribution.
What do you mean by the residual plot here?
Well, my understanding is basically the predicted value minus the actual value, and then see how that distributes.
Oh, I see. Yes, there's the amount of error here. Yeah. Yeah.
Well, very impressive. Thank you.
Thank you. Thank you all. I really appreciate it.
Thank you, Dr. Ashour. I do not see any other questions in the box, so I think we can end this meeting for today. Thank you so much. And this will be recorded and on our website in a few days. Thank you all and have a great afternoon.
Thank you. Have a great day.
Have a good one.